Oh, you have to, you disabled screen sharing.
Oh, my bad. Yeah, I think it's just the auto. It's like the auto feature.
Yeah.
All right, you should be good.
All right, cool.
You're trying to be a good student like Stuart. Take some notes.
Nice. Okay, all right. So decision trees. So basically, like the premise of decision trees are, it's like you have a bunch of features that you're trying to determine some useful information about, and it's all about just like figuring out where to split your data so that you can eventually whittle it down to get uh, a classification. And so, yeah. So let's take a look here about like, so this is the visual of a decision tree. It's no different than just like a tree. Um, Well, basically, what you're doing is you're partitioning your data into different groups, and each, like, you have to ask a certain type of question, like a yes or no question, or uh, you need some sort of like understanding of the data that you have and the end goal classification, so that you know how to split, like what questions asked to relate to properly split your data into groups. So when you're trying to distinguish homes from in New York versus homes in San Francisco, you might have a data set that includes like uh, color, the shape of the house, architectural style. Um, I don't know, like the slant of your roof, uh, whether it has a basement or doesn't have a basement, and you take all of that data, and all of that represents a house, whether that house is in New York or San Francisco, and you ask certain types of questions about certain features so that it helps you group rows of data. So, I might ask like, uh, does the home have a basement or not have a basement? And then I would group my data. Uh, I would take all of the data that for homes that have a basement and move that to the left. And then if the answer was no, I move the groups that didn't have a basement to the right, and then continually ask questions until I can whittle down to a pure group that would be like, okay, uh, this is a home for New York, or this is a type of home. All the homes in this group would be homes in New York. All the groups of Yeah, all the data points in this group are homes from San Francisco, and then you can use that same like series of leading questions to eventually evaluate new points as you get them. Does it make sense? It'll make sense when we look like at the examples.
Mhm.
Um, Yeah, so here's another example of decision trees. So your four features that you have is the outlook, the temperature, humidity, and the wind. And then you have the outcomes. And the question you're asking is, will I play tennis today? So what you can do is look at uh, all of the data for outlook. So whether it was sunny, overcast, and rainy, and see what the outcome was for that. So um, and you can do that same process for all of them and see what the outcome is, and you can build a decision tree based on those questions. So your dependent variable, so the thing you're trying to find out is, am I going to play? So you saw, like, counting the number of like the output labels, you saw that there were 9 instances where you played and 5 instances where you didn't play. And then you're asking about the outlook. So you pick outlook as the first question that you wanted to ask. What was the outlook for all of the data? So on sunny days, we had 2 days or 2 plays and 3 not plays. We had 4 plays and 0 didn't play. And then on rainy days, you had 3 play and 2 don't play, right? So when you have an impure class, so like overcast, for example, is a pure class. It means that uh, your decision tree would if it was introduced to new data, if you're if that data point, if the outlook for that new data point was overcast, it would automatically classify it as a go ahead and play day. So when you have impure data classes, you'll need to continually find new splits on additional features in order to come up with a clear group consensus. So if we look at sunny, for example, you had 2 days that you played and 3 days that you didn't play. So we introduced a new feature, which is now humidity. and we're going to ask what you arbitrarily decide what the humidity level should be or something. Like they made it 70. So if it was less than 70, let's take a look. Um, so if it was less than 70 or equal to 70, 2 days you played, well, 0 days that you didn't play. So here you've now got a pure class. So uh, you would run, if you got a new data point, you would run through this example, and if it ended up in that if it has those two features, then it would say that it's likely that you would play, and then you repeat that process for all the others. So it's kind of very sequential in the logic. So it's like you start with looking at one feature at a time, see what the outcomes are like, and then you continually add new features until you get to a pure class. Any questions? All right, cool. Yeah, so decision trees, the pieces of decision trees, you want to find the best attribute to split on, and then you want to find the best split on the chosen attribute, and then you have to decide when you want to stop splitting. And so we'll quantify what best attribute means and what best split actually means um, down below. Yeah, so this is just another example. So you can have categorical or discrete attributes, which is just another classification uh, or classification based outcomes. So here you've got your input variable. Your input data has three variables. You can have your hair, your height, and your country. Those are your features. And then output label is whether you come from Gromland or Polvia. So you're trying to classify if you're given these three attributes, where is this person from? And so you've got a training set with the two features you're looking at, the height and the hair of the person, and then the outcome labels. Again, you're doing the same exact thing where here you have your initial total data set. So you have two people that come from Polvia, four people that come from Gromland. You picked hair to be the initial best or the initial feature that you no, let me get the wording correct. The best attribute to split on. So you determined that hair was the best attribute to split it on. So you split your data, and then you see that if you have dark colored hair, you're most likely a person from Gromland, and that's a pure attribute or a pure category. So that would be a leaf. You stop there. However, if you have blonde hair, it's 50-50. So you're going to need to split on the next best attribute to train on or to classify on, or I mean split on. So uh, you introduce the height. And so whether you're tall or you're short, and you can see that there's a clear split between whether you're tall or short in the country that you come from, and then you end up with the output classifiers.
Okay, my question is this an example of a categorical or or discrete sorry, attribute?
They're the same. Like, so it's not that it's categorical or discrete. Categorical variables are discrete in nature. There is continuous there are continuous random there are continuous decision trees that basically try and categorize regression, but they're not very good at it, if that makes sense. And it'll talk a little bit more about it down there.
Okay, that makes sense. Thank you.
Yeah. So yeah, random forest or not random forest, but decision trees are generally stronger at categorical classification problems, but they're not overall very good at classification anyways, on the whole. But in the next lecture, you'll see that like you can take a decision tree and build something called a random forest, which is a collection of decision trees. And so individually, decision trees are weak on classification, but a random forest is actually a very strong predictor of classification. So what you can do is take a bunch of these weak outputs or weak predictors for classification and aggregate them together, and you'll get a decision forest, which is actually very strong at that. but we'll talk about that more. Yeah, so you can see here, like at each level, so we split the tree, or at each level of the tree, we split the data according to the value of or on one of the attributes. And after enough splits, only one class is represented in the node. So this is called a terminal leaf of the tree. So we call that class the output class for the node. And that's ultimately what we're trying to go for. Make sense? Yeah. So here's like the general decision tree structure. So you start off with all of your data, and then you pick the best attribute, x1 in this case, um, to split your data on. It will then group things, and then depending on how well of a split or predictor it is, uh, you'll eventually lead to the leaf nodes that have the output classes. Okay, so this is a good, like this is the rest of the lecture is just an example of a decision tree. So here we have two features. We have x1 and x2. And so you can see that we have, in total, we have 7 red dots and 4 green crosses. So in this example, we've chosen x1 as the best split feature. So we're looking at whether x1 is greater than 0.5 or less than 0.5. That's the question we're going to ask. So we ask if the question, or we ask if x1's values are less than 0.5. And looking at it, by the way, the actual like diagram to the left over here with the boxes and the splits, normally what you do is you have x1, you have the feature x1 and its probabilities on the x-axis, and you'll have x2 as a feature and its probabilities on the y-axis. So you're looking at like the probabilities of those things. So you can see that if the value of x1 is below 0.5, you can see that you have 3 red dots, and then you have 4 green crosses or x's. And then if you have a greater than 0.5, it's all red. It's all red red dots. So that is actually a really good value to split on because there's very little uncertainty. There's uncertainty in the distribution of samples. So then for values that are less than 0.5, you'll need an additional split. So now you're going to be looking at x2 as the next thing to train on. So if x2's values are below 0.5, here again we get 3 red dots, so it's very clear what the output classification would be for it. And then if you're above it, you get 4 green crosses, so it's very clean. Now, this is actually just the same thing. So the class of a new input can be classified by the following tree all the way down to a leaf, and by reporting the output of the leaf. So um, this distribution basically means that if I get new data involved after I've already built the tree from this test data or training data, as long as I have a point, a probability for x1 and a probability for x2, I can always determine what that value will be. So I can be told, I don't have to know if it's a red dot or a green cross. All I need to know is the probability for random variable 1 and random variable 2. And using the decision tree, I can arrive at what the outcome should be for it. So here you can see 0.2 and 0.8. We determined if you just follow the decision tree, 0.2 is less than 0.5. So we go to the right. We go to the left. And then you're looking at if x2 is greater than or less than 0.5. And we have 0.8 for x2, so it classifies as a green cross. Okay, yeah, so here's continuous attributes. So we're looking, this is different. The structure is the same basically, or like the concept is the same, but this is now based on time. They didn't really go into depth about continuous attributes for random decision or for decision trees, but
What were we doing just a second ago? Wasn't that continuous?
no, these are discrete.
Oh, these are discrete?
Yeah. Oh, I guess I don't. Oh, actually, you might be right. These might be no. These are continuous. These
Okay.
are continuous because the probabilities are fluid.
Yeah.
Yeah. Yeah. So these are discrete or these are continuous, but they behave. You can see that there's very little difference in. It's just a matter of whether your probabilities are fixed or if they're fluid in a like random variable,
Mm-hmm.
right? Because if you look at like uh, with discrete things, you actually have like you're not basing it on the probability of each thing. You just discrete, like you just say this. I have two of this and two of that, and you just like you just show it, right?
Mm-hmm.
Um, yeah, like in this example, it's like you have a fixed number of items, and you're using the actual like the count of how often they've happened, not the probabilities of them. So here so this, yeah, so these are the continuous trees. But yeah, important questions to ask. So how do you choose which attribute or value to split um, on at each level of the tree? And then when do you stop splitting? Uh, is it the case that every leaf should be a pure class, or will you? What do you do in this situation where a leaf is impure? How do you assign the class label? And then if it's too large, how can it be pruned? So there is an issue. You sometimes like random trees, or not random trees, but just decision trees in general, can become too large because you can have like imagine you have like 100,000 features, and each feature has 1,000 points in it. That becomes a very very large tree, um, and you can overfit. So that's another issue. But we'll talk a little bit more about how you actually split. Um, Yeah. So first off, like you have to pick the best feature to split on, right? So you need to determine which of your attributes are the most important, and how you determine what's important is specifically looking at which one gives you the most information. So in this example, you can see that you've got 5 red dots and you've got 6 green crosses, and you could split along the x-axis or you can split along the y-axis, but you have to figure out which one numerically would provide you the most useful split. Here you can kind of just visually looking, you would rather have a vertical split somewhere, so you would probably want to split on the x-axis, um, as opposed to a horizontal line splitting your data because it would be more mixed. Yeah, so here's a visual depiction of what I was just talking about. So if you do split on x1, you're introducing a vertical line, and you can see that you get a pretty clean split between classes. But if you supposedly wanted to split initially on x2, you have a horizontal split between your data, and you can see that it's a very mixed and a bad classifier. So you want to find the most compact, smallest tree size. And I've seen this term Occam's razor before, but I didn't look it up, so I need to refresh on that. But the concept is the same. Basically you're just looking to find the most efficient representation of uh, a tree that could classify the data correctly. So you wanna pick the splits that will get you to the fastest node. The fast will get you there. Will get you to the fastest. Will get you the fastest two peer nodes. I can't read. Um, okay, so um, again, you can visually see that like you picking x1 is obviously the fastest method to get to pure leaves, because you've only had to split once, and you only need to split one more time to get there. Um, yeah, so the information theory is actually like the is how you determine what features you want to split on. Uh, yeah. So remember, entropy is like uh, how uncertain your data set is, right? Entropy has the highest like the variance is high for things that have high entropy. So what you really want is you want to gain higher information. So you need the lower the more you reduce the uncertainty, the higher the information gain will be. And so as a result, you would want to select the least likely events to happen because they will have the highest information and the lowest entropy. So if you see like a coin flip here, you can if you were to have an event where you rolled a coin 6 times, or you flipped a coin 6 times, and all 6 of them were tails. Here you have a probability of 1 that you got tails, and a probability of 0 that you had heads. So if you remember, p log p is the negative sum of p log p is the entropy. So this would give you an entropy of 0, and as a result, you would have the highest information gain because the information gain is like inversely proportional. So you always want to select your features. So the initial determination of whether I pick x1 or x2 is determined based on whether that has the lowest uncertainty, because it would lead to the highest information gain. Does that make sense?
Mm-hmm.
So on every time you split your data, you will look to find the most information possible.
Wait, no,
Yeah.
no. I think we're minimizing.
You're minimizing entropy.
Okay, I see.
Yeah. So in general, the average number of bits necessary to encode n values is the entropy. So if you remember, the Occam's razor is all about finding the most efficient representation of your decision tree that reflects the training data. So you will want to find the lowest number of bits required to describe your training data. And again, that's the lowest entropy. So yeah, a high entropy is that, all classes are nearly equally likely. So it would obviously be a very bad classifier because it's no better than guessing. A low entropy says that a lot of these classes are very unlikely, and a few classes are very likely. So imagine you have a feature set of 10 random variables. You would effectively just want to select a random variable that had the lowest entropy across all. So you need to be calculating information gain at each split. So I have 10 features. I calculate the information gain for all 10 of those, or the entropy. The one with the lowest entropy will be the one I pick to split my data on. Then I have now 9 potential features that if I have impure classes, I will continually calculate information gain, and it goes down until you get pure classes. That makes sense?
Mm-hmm.
Yeah, so here's another good diagram. So basically the frequency of occurrence or probability of the event, and then the class number, which is the output label. So the higher the entropy, you can see that they're all equally likely. And so that would probably be a very impure, it's a bad classifier. But here you have all very low likelihoods for most classes except for one. So as a result, that has a really low entropy, and actually pretty high information gain as a result. Yeah, so if you see like here, you've got entropy of 1 and you're calculating entropy of 1 and entropy of 2, determining if the probability of A is the thing you want to split on, or random variable A is what you want to split on, or random variable B. And so here you've calculated the probability of A occurring versus the probability of B occurring. So you calculate the entropy of H1, and that gives you 0.59. You calculate the entropy of H2. So for this distribution, you see that you get 0.97. And so H1 is less than H2. So 2 is less pure than 1, which is, you can see just from the visual depiction. So conditional entropy, you're just looking at the entropy of your left side and the entropy of your right side, and it should sum to the entropy of the parent node. So yeah, after splitting a fraction of your a fraction probability, or PL, of the data goes to the left and has entropy HL, and then the fraction of your data that goes to the right or the probability of the data that going to the right has an entropy HR. So does that make sense? You can only have as much entropy as the parent node or the root node, right? Because that's the total representation of your data. So when you split your data, you're going to have fractional entropies that should sum up to the total or be less than or equal to the parent node. And so information gain works the same way. So we want nodes to be as pure as possible. So we want to reduce the entropy as much as possible. We want to maximize the difference between the entropy of the parent node and the expected entropy of the children. So basically, we want to be able to determine if we have entropy, we have capital H entropy of the parent node, and all we're looking to do is to minimize entropy for its children, because that means we will gain the most amount of information, and the ambiguity of your data split will be reduced. So you can start to be more certain about what the contents are of your children nodes, and that makes sense, right? That's pretty logical.
And this obviously extends for more than a binary split, right? So it's
yes, exactly. So in situations where, like I was saying earlier, if you have an example of 10 features for a data set, you'll have the total entropy of your original 10 features summed together, and that'll be the total entropy of your system. So then you want to pick the feature to split on out of the 10 that will have the lowest entropy for its children nodes, or the highest information gained. And then you continually repeat that process until you've used every single feature, or you've gotten to the point where all of your classes are already sorted to be pure, which may happen earlier than you using all 10 of your features. Ideally, that is the case, and you don't use all of your features to determine your classification, because that will tell you that some features are unimportant, and then you'll gain information from that. Yeah, so we want to maximize the difference between the entropy of the parent node and the expected entropy of the children. And so the information gain is the amount by which the ambiguity decreased by splitting the nodes. So so earlier, like I was saying, you have the total entropy minus the conditional entropy of your left-hand tree and your right-hand tree. Those are just notations. We've already gone through that stuff. Here's another example. So if the total entropy of your system is 0.99, your information gain calculation will be the entropy of this total system minus the entropy of the left and the right. So you can see that the entropy of your left-hand side was 0 because all of the dots were red, and the entropy of the right was 0.58. So that gives you, so that would be the most information gained. And then on the right hand, if you chose to split across on the y-axis or your random variable x2, you can see that the partial calculation leads to an entropy that's very high on the left and an entropy that's very high on the right. And so you would not want to select the right-hand side option, because you can tell that the amount of information gained is very low between the parent node and the left or the right child. But you can see that you gained a ton of information on the left-hand representation by splitting across on x1. This is like probably the most like straightforward lecture, I think, of all the topics we've learned so far, but it happens to be the most useful.
Is this going to lead us into neural nets?
Yeah, next week's lecture is neural networks.
Awesome.
Yeah. Random forest we'll learn about, but decision trees are actually utilized a lot in production systems today, like in industry. A lot of healthcare, like a ton of healthcare, like disease diagnoses, happens through through decision trees. Mm. Yeah, so you can see like here.
Kevin likes it.
Yeah, it's super useful, and it actually is fairly logical. So yeah, you can see that you gain 0.62 2 bits of information on average by splitting your data as opposed to 0.05. So it's very clear that you would choose your left-hand side split. Yeah, again, information gain is greater, so you'll pick to the left. Here's a more complete example, and so this is just a random sampling of 20 data points, training examples from class A and 20 training examples from class B, and you have x1 on the x-axis, and you have the probability of x2 on the y-axis. And so you're looking at, this is a continuous example, a continuous random tree. I keep saying random tree, but I mean discrete. The random tree stuff we'll see in the next lecture. Yeah, so you have to calculate the information gain. So you're running through the example we just saw in the previous slides, where you have the total entropy of your system, and you'll need to calculate the conditional entropy for splitting across x1 versus splitting across x2. And this is describing that, sure, if you were to select x1, then you do the math, you will have an information gain of 0.13, and the location at which you want to split the probability should be 0.24. So you can see that they've drawn the line, the vertical line, choosing x1 as the best split, or is the best attribute to split on, and the value is at 0.24. So you can see that they've created a whole class to the left that's purely red dots. And so that is a good split because you gain a lot of information.
Question about this. Not particularly about this slide, but when you're doing this, can you formulate it as like an optimization problem, or you have to like literally iterate through and calculate the information gain?
Yeah, so if you have a really small data set, you just enumerate through it. So it's like you do calculate the information gain for all of your attributes. But if you have a really large one, so if you have a lot of features, then it would be computationally intensive to be calculating information gain for all your features.
Mm-hmm.
And so as a result, that's where random forest or like random decision trees come in. You're able to use we'll talk about it, it's called bagging, but it's a technique that you use to reduce variance, introduce randomness into your system, and select a subsample of features. And so that subsample allows you to still have to compute the information gain for all of your features, but it's a smaller subset of features, so it's not computationally as intensive. Does that make sense? It is a minimization problem. They do the same thing. Like you iterating and calculating the information gain is minimizing the entropy of the system.
Mm-hmm.
Does that kind of answer it?
Mm-hmm, mm-hmm.
Okay. Yeah, so they've determined that x1 is the best attribute to split on. Here's the information gain for it. Now you can see, now you're looking at the next split. So this is x2. So if you were to select x2, you can see that the information gain for x2 is 0.202. And x1 was 0.13. So you actually will select to split on x2 first because it has the higher information gained. Yeah, so you can see here, they almost have the same probability values. You're splitting almost on the same probability, but you're looking specifically at information gained. So they determined that x2 is the better value to split on, or the better attribute to split on. So now you're looking at whether your values for your data are below a probability of 0.23 or above a probability of 0.23. So you take all of the data points that are less than 0.23, and you store them in a child node or like an array or something, and they stay to the left. And the rest of your data is then goes to the right. Now you have to select the next best attribute by calculating the information gain for that, and figuring out which probability would be the best place to split on. So now you have 13 Class A examples and then 20 Class B examples. So you'll need to split again. So here, there's to the left side, you have a pure class, so you don't need to split any further and return it as a leaf node with output A. For the right, your data point is not, or your class is not pure yet, so we'll split further. So here we do a split on x1, and you'll calculate a split on x1 and a split on x2. For every time you do this, you'll want to calculate whether, like, which data point or which variable you're wanting to split on. You'll calculate the information gain again. So, but with a smaller subset. So here they calculate the information gained for x1 if the attribute value was 0.22 or probability was 0.22. So you get 0.18 information gained. And if you selected x2 and you picked 0.7, they identified the best value as 0.75, and the information gained from that was 0.35. So do you see, like, the only thing that's fixed between these two slides, like these two slides are the evaluations for each step. So you can see that, like, the only thing that's constant between these two is that 0.2 horizontal line that was selected because of your previous step. So now what you're doing is you're trying to determine, do I split again on x2, or do I split again on x1 with a new horizontal line, or do I split again on x1? But either way, you've subtracted out the data that was classified from your previous, and you're redoing it. So it's just it's a recursive problem. Like, you'll want to do this as a recursive strategy, because you'll eventually get to a leaf where you can terminate your recursion. So yeah, you're calculating the information gain. You see that you gain 0.35 by splitting it again, splitting on x2 instead of x1 again. So you can see you've gone x2. If it's greater than 0.75 or 749, you get a pure class of 7 class A variables. So it's another good split. And then you have another impure class to the left. So you'll split again. So here, there's no, like they're saying, there's no further point in splitting this node because it contains data from a singular class, class A. So just output that. But for the impure class, you'll want to split again. So they speed it up by doing, there's another 2 splits required, and they do the math again. But you can see what the final split looks like for the decision tree. You have all of your X's boxed in, and you have all of your red class A examples on the outsides of the boxes, and they're all properly classified. Everything is pure.
You know, this is interesting because I just assumed that you only split along an attribute once, but I see that, and especially for a continuous, you might split on the same attribute several times.
Yeah.
Computationally intense. That kind of sucks.
Yeah, it is computationally intense. But the thing that I realized when going through this is that that assumption makes it, or if you understand that information gain is the rule of law in how you make your decisions. If information gain is what actually drives your decisions, it leads you to, there are situations where you actually will split on the same variable multiple times, even consecutively, because it would provide you more information, and that's not immediately intuitive. Like I would have, like, initially before doing this, I would have thought, okay, I picked x1 and it told me to split this way. I would have thought, let me go split on x2 now to get more data. But there are more, it's just as frequent that you would want to split on the same variable multiple times, because you would actually gain more information as a result of doing that. So yeah, it's kind of cool. Yeah, and so once you have your decision tree, it's pretty trivial. Once you get new data, you just follow the decision tree based on the probabilities of your input data, and then you'll eventually be able to output or a classification for that data point. So yeah, they do 0.5 and 0.5, and you could just follow the track until you get to a classification. I think they might have messed this up with the errors, like the direction of the symbols, because x2 x2 is greater than 0.5, so you go this way. But they have x2 as something, you see how like x2 is less than 0.5 or less than 0.2?
Yeah, I mean, I think I think they've characterized the split as always sort of going left for the split value. So x2 less than 0.23 always goes left, and then you see x2 less than 0.67 always goes left, and then so on and so on.
Yeah, but I was trying to, does that still work though if your x and y values were 0.5?
Yeah, it does. The directions work.
So you're saying that, so what they're doing is that uh, if this inequality doesn't hold, you go to the right.
Yeah.
Yeah,
Oh, okay. That's a weird way to write that.
yeah, but
It's not like mathematically intuitive.
yeah, I mean, they could have written it on both sides, but who cares? Yeah.
Yeah, okay. So yeah, so now you're looking at these questions again. We're trying to, so we've answered the question of how do you actually decide which attributes to split your value on each level. So now you got to we ask the question like, when do you stop splitting, and when should a node be declared a leaf? And then if a leaf node is impure, how should the class label be assigned? Yeah, so pure and impure leaves and when to stop splitting. So you you stop splitting when all of the data in the node comes from a single class. So that makes it obvious. You will declare we would declare that node a leaf, um, and we would stop splitting at that point. And then that leaf should just output the class of the data that it contains. Um, However, when you have impure classes, so if several data points have exactly the same attributes, even though they're from different classes, you wouldn't be able to split any further. So if you kind of see like the example above where the real world example they had where you had 20 data points from class A and 20 from class B, what you look at this example in the left, bottom hand left corner, you've got four variables from 4 data points from class B, um, and then you have 2 data points that actually belong to both classes. They're right on top of each other. So because they're from both classes, you can't really split the data cleanly. So you would just label it as a leaf and you go by majority rule. So you would just count how many classes are from class B purely, and then how many are from class A, and whichever had the majority, you'll output that label. That makes sense.
I have a slightly different interpretation. I think it actually, those red dots are actually from class A, but because all the other attributes are the same, they're just gonna say fuck it. It's class. It's class.
Oh, okay. Yeah, you're right. You're right. That's more logical. Yeah. Oh, I wish they'd it would have been a
Or
little
like an
more.
animation or something.
Yeah, exactly.
Yeah. Okay, but that makes sense. So here's the pseudocode, or the pseudocode for this algorithm. Basically, your learned tree is you'll have an input that's a set of x of r training vectors. So each contains the values x1 through xm of m attributes, x1 to xm. So your random variables x1 to xm, the capital ones, are your features. So that could be like location, house, like for the pricing, for the housing example, it could be like your basement. Does it have a basement or not? It could be a vector representation of that. That could be x1, x2 could be like pricing of the home, stuff like that. But basically, you'll get an input, a set of x of r vectors. And then the vector y is just going to be your class outputs, the output labels for those data points. So if all of the data points in X have the same class value Y, then you have a pure leaf. You return a leaf that predicts the Y as that output. And that makes sense, right? What they're saying, they're saying that all the data points in X all are mapped to the value output label of Y of J. Now, if all of the data points in X have the same attribute values, then you'll return a leaf that predicts the majority of the class values. So that's saying that um, if you have all the data points in X and they all have the same attribute values, which would mean that they all belong to the same features, I believe. That makes sense.
Yeah.
Then they're going to be a mixed class of. It'll be a mixed group in the leaf, a mix of data points in the leaf. So because not all of those data points belong to a singular feature. So then you'll use the majority rule and calculate which had the highest number of how many data points belong to a singular feature. Does that make sense?
Mm-hmm.
I'm a little confused by it because for our continuous example,
Yeah.
like, I doubt they'll have the exact same value, but they might have the same attribute value relative to like some threshold.
But yeah, that's what this means though. That's what this is saying. Like in a continuous example, you created the splits, and so it's just saying that you have all these data points that are have been grouped together, but some of them have like different y values, right? Like the output label would be different for some of them. They all belong to different parts of. They all have the same attribute values. So like say like it's I split it, the last split of this group is on like they're the green crosses or something, or no, that's the apple class. But say like the probability of it being a green cross is like, I don't know, greater than 0.75. So I had other other attribute values. Actually, this is not a good example either.
Well, I guess can you scroll up one? Because I think, do you have to define a threshold then? Because if you look at the bottom left and you see that like these values are about the same, where like the x, I guess the direction on the x-axis, like they're pretty close, but they're not the exact same. And similar thing with the y, right? And so for that second condition, we're saying like, hey, are all these and what are all the attribute values the same when you compare x and y sets? Like if it's continuous, how do you say that two attributes are the same? Does that make sense?
You're saying because you could always make more splits.
Yes.
You can basically make an infinite amount of splits.
Yes. That's what I'm saying.
Yeah.
Or is that like in the weeds where it's like, oh, by the way, if we're doing this comparison, you need to have this in there.
I mean, it makes a lot of sense for discrete, but for continuous, I feel like you can always split more.
Yeah, because you would end up creating like infinite slices or infinitely small slices, or like splits.
And that might be overfitting. So
that would be that would be overfitting. Yeah, I think maybe I don't really understand it.
I feel like this code, the pseudocode, that second if statement should say if all data points x have the same attributes, value, whatever. Like you have two options, then you could either split again, or if you're basically done, if you have some threshold that you've hit, if it's discrete. Well, if it's discrete, if you've kind of gone through all the attributes, then you're done. But if it's continuous and maybe you have some threshold or some maximum iteration that you want to do, then you stop or you split again.
Yeah, that makes sense. I don't know. I need to look this up. I was watching a lecture on this earlier this morning actually, because I didn't have that much clarity about what they specifically meant. The problem was that there wasn't an example. I hadn't gotten to the example of where they actually run through the pseudocode. But let me get back to you guys on it, because I know you're not supposed to split past a certain point, because again you get to that you get to the point where you have like the infinite splits. You could just keep splitting it forever until you get pure classes.
Maybe the threshold we're talking about is the threshold t in the pseudocode.
Oh, it could be. Yeah, if you see like threshold t, so you can try all possible attributes x of j and threshold t, and then choose the one j star for which the information gained of y given xj and t is a max. So yeah, I guess that's the case. So this is basically just saying that you're going to try all of the different all of the different features that you have in your thing, and then the thresholds for you, whatever threshold you select, and then choose the one that gave you the maximum information gained post split. So x of L and y of L is the set of data points for which x of j is less than t, so the left side of the tree, and then x of y of h and x of h and y of h are the set of data points for which x of j star is greater than or equal to t, so that would go to the right. And then you recurse by calling left child, and then learn tree, and then right child learn tree with the subsets, and eventually return the whole tree, the root node.
Oh, that was for continuous. Can you go back up again? I'm sorry.
Yeah, this is for continuous.
Oh, that's why we have the threshold t.
Yeah, so the threshold is a hyperparameter that you'll have to determine. And actually, I think they do write down how do you select that that threshold t. So there's like a rule of thumb or something for it. So yeah, this is the continuous stuff. Discrete's a lot simpler. So it's the exact same thing. You get the set of x of r training vectors. They all contain values x of 1 to m. And then you have the y of r vector, that's your output labels. And so if all the data points in x have the same class value y, return the leaf node that predicts y to have y as the output. And then if all the data points in xr have the same attribute value, x of 1 of m, or x of 1 to m, then return a leaf node that predicts the majority. This time you don't actually have a threshold.
Mm-hmm.
Again, this also splits. This also allows you to have an output, a class that just is based on the majority. So I'm trying to figure out why you stopped.
Can you go back up to the threshold thing again?
Mm-hmm.
Okay.
I didn't realize x and y were like the data versus the class, but I think that makes a lot of sense. Okay.
Yeah. So yeah, x and y. The capital X is like the feature, and then the data points within the feature are just lowercase x.
Yeah. Thank you.
Yeah. So here you would try all the possible values of x of j, the feature, and then select the feature that would give you the maximum information gain. And then for every possible value of v of x of j, so all of the data points contained within that selected feature, x and y are the set of data points for which x of j star is equal to v, and corresponding classes. So for this, remember what I was saying, discrete decision trees, instead of having a threshold t that you figure out, it's really based on the questions that you're trying to ask and how you numerically represent that. So if I ask a question like, is my house blue or is it red? That's a yes or no question. So you're looking at v to be either a 0 or a 1. So that's how you select your values of v. It's conditionally, it's holistically dependent on, or like wholly dependent on your question that you're asking. Because all of decision trees are not general. They are general, but you apply them to your specific problem and the specific data set that you have. So that's part of the art aspect of it, is that you need to figure out what questions are useful, what questions should I be asking, and how do I use that to split my data. And usually that returns you your value v. And then you do the same thing. You calculate the child and then recurse there, and then return the root node. So here's a summation or a summary of it. Given n observations of training data, each with dimension d, or d attributes of x and a class attribute of y, you'll construct a sequence of tests, the decision tree, to predict the class attribute y from the attributes x. So this is a good this explanation it makes it clear in seeing how like hospitals and doctors will use decision trees to diagnose patients based on symptoms, yes or no questions of symptoms. Um, Basic strategy for defining the tests is when to split. You're always looking for maximum information gain on the training set at each node. So now the problems that come up with decision trees, the computational issues like how expensive it is to compute information gain, overfitting like we said earlier, and then pruning, which is just deleting nodes to maximize information gain.
I have another question, which is,
Yeah.
I'm thinking about the hospital in particular, where you probably have a mix of categorical and continuous data. Like your temperature and heart rate might be continuous, but like a
Right.
rash or like bleeding might be categorical or something.
Yeah.
Um,
Well, you can reframe continuous variables into discrete categories. So you'd imagine temperature.
yeah,
It's rethought of as, does he have a fever or not?
yeah.
And that could be categorized as greater than 0.105, like greater than 101 point whatever, or less.
I just wasn't sure if you can make a robust decision tree to handle multiple types of data, or
You can.
you know.
You actually, one of the things that you can do is create a random forest,
Oh,
which is a set of random trees. And what you can do is have some be discrete while some of them are continuous. However, like earlier, I was saying that random, like random decision trees aren't very strong at uh, continuous or continuous data for anything other than classification. They're weak at regression. So um, you may end up having a weaker classification, eventual classification, if your goal is to determine a specific disease or specific class. Um,
Could
it's
you
actually it would probably be stronger for you to stick to like wholly discrete random trees.
yeah.
Mhm.
So if the leaf node is impure, how should the class label be assigned? We just answered that. And now if the tree is too large, how can it be pruned? So trees being too large, this is meaning that you have too many branches and too many leaves. So you'll lead to overfitting. This is where we're talking about you do the splits. If you do infinite splits or you split as many times as you want, you can overfit. And then you have high variance, um, because again, the information gained after doing too many splits will be minimal, so the entropy will be very high and the variance will be also high. So that will make your initial the initial data put into that, the predictions will be bad. So how do you avoid overfitting? You actually just acquire more data, which is always the answer. The better your prediction, if you want better predictions, more data. That's always the answer. Um, you can remove irrelevant attributes, which is a manual process. So you could look at your data tree and see that, oh, this actually is kind of not important as a feature, um, which is you knowing what you're looking for. So you'd have to already know what you're looking for and manually go through the tree. You could grow a full tree and then post, you could prune it in post, which is again very similar. Um, I guess, well, it's not similar. The point before this is saying that I have a set of 10 features. I know that this one's irrelevant, so I'm just going to leave it out and I'll look at the first 9. Versus this other one, which is saying I don't know which of these is irrelevant. Let me make the whole tree, go through the whole process, and then look at it and see which one's useless. Um, and then ensemble learning, which is the next lecture, which is the solution to this. Reduced error pruning. You can take your original set of data and split it into a training and validation set. So you will use a smaller subset of data to produce a tree, and then use the remaining data to train or to evaluate based on error how good it is. And then you use that calculated error to determine which leaves you should remove to reduce the error. So you'll split it into training, you'll grow the tree based on the training set. You do until further pruning is harmful. You'll evaluate the impact on the validation set for each possible node and those below it, and then greedily remove the nodes that improves the validation set accuracy. So we'll look down here for a second. Pruning of the decision tree, it's done by replacing the whole subtree of the left of a leaf node. The replacement takes place if the decision rule establishes that the expected error rate in the subtree is greater than the single leaf. So the example makes this more clear. So if you have an example where you're looking at color and you could either be red or blue, you had in your training set 1 positive for red and 2 negative for blue. And that's just from 3 total data points. The actual label was 1 positive and 2 negative. The predicted label was 1 positive and 2 negative. So you have 3 correct predictions and 0 incorrect predictions. Now we take the rest of the data we had for the validation set, and we do the same exact split, or we do the same exact, we run it through the tree. So in the tree, you see that you had 1 positive and 3 negative, and you had 1 positive and 1 negative. So out of 6 validation points, you see that 2 of them are actually labeled as positive and 4 are labeled as negative, but your predictions said that there were 4 positive and 2 negative. So that means that you had 2 correct answers and 4 incorrect answers. So as a result, you would want to prune this branch. You would want to get rid of it because it has 50% more errors. Does that make sense?
Which branch?
So
the red branch?
You're imagining this is a leaf.
Like okay.
This is a branch, like a branch of some higher thing.
Okay.
Right. So you would imagine like on this level, there would be multiple of these decisions. So this one's specifically looking at color. Maybe there's one that specifically looks at like shape, another one that looks at like whatever. And you're evaluating whether you should prune everything that's tied to color. And you can see that the error as a result of using color based on your validation set is really high, right? Your training got 100% accuracy, but your validation had got only 2 right out of 4. So that's what, like 2 out of 6 wrong. That's 33% error. So you just prune it all, get rid of it.
I think it also, like, you would have less error without it at all.
Yeah, that's the other thing. So you're looking at, if I use the whole data set for this branch, what's the error? Or like what would I predict? And then if I use it as a split, what would the error be? So you can see that you'd have more error you'd have less error if you got rid of it. Cool. So this is the end of this lecture. The next one's really short, like much shorter than this. So I'm just going to go straight into it, because they kind of just lead right into each other. So ensemble is how you protect against overfitting, and then the high variation. So it's a technique. Yeah, so this is saying, like, what classifier to choose. You can go from the simplest model to the more complex model until you get the desired accuracy. You could discover a new model if the existing ones don't work, or you combine all the simple ones together and try to get a high accuracy that way. But let's talk about bagging, which is called bootstrap aggregating. It was originally designed for combining multiple models to improve stability. This is the introduction of randomness into your total sample. The idea of bagging is that you have a total data set of samples of data points. And what you're doing is that you're selecting some random subset of them, but still comprised of the same dimensions, original dimensions of the full data set. So if I have an X and Y coordinate, and I have a set of 5 coordinates, the bagging strategy says that I should create a new set, S star, that uses X star, which is basically, I still want to make sure I have 5 coordinates, 5 data points in my set. But what I'm going to do is randomly select those 5 from the original. So I can have duplicates, I can have whatever. And I use that that randomness is what you introduce into to create a more general decision tree. So if I have 5 data points, I would create a set that includes 5 data points from my original sample, but they would be random. They would be randomly selected from that. So I'd have duplicates or whatever, and you would create a decision tree from that. And that helps protect against overfitting and the variance issue. So you can see like here, it contains 3 out of the 4 original sample values. So you have the first row. Yeah, so you get that. So yeah, here's in pseudocode, it's saying consider the sample set S that is X of I and Y of I. So you're gonna pick a sample S star with the replacement of size N. So that's the bootstrap sample. So you can determine how many of the values you want to replace from the original set to create a new set. You're going to train on S star to get a classifier F star. And then you'll repeat it B number of times, which is going to be the number of times. I think you could do it as many times as you want up to, I think, size of N. I think you would probably want B to be less than or equal to N. Because that would just mean that I could say if I have 5 data points in my set, I could create 5 samples, 5 random samples. Eventually, that would have diminishing returns because you would start predicting. You would start selecting sets that comprises of something that you already had. Does that make sense?
Yeah.
Yeah, and your selection of these data points follows a uniform distribution. You just want to use a normal, not a uniform. Use a normal. So you'll repeat B number of times to get F of 1.
Oh wait, the selection of which data point?
Oh, meaning like the random value. So like I want to pick, if I what I'm saying is the number
Like
of
picking,
times.
like are you saying that the picking of the samples should be using a normal distribution?
The picking of the samples? No, I'm saying
Okay.
the number of times that you pick follows a normal.
Okay.
So like
The repetition, basically B.
yeah, B. I'm still in the lecture. I'm still in that lecture, like the video I'm watching. And so they said just assume using a normal, so that your random value is not like, you want your random value to differ enough. Does that make sense?
No, I'm still
I don't understand what the normal distribution would be over if you're just choosing some number, some integer B.
Actually, you know what? Forget it. I think I might have misunderstood. That might have been something else, or like for something different. Just forget that and just go straight with like pick a random number N that's going to be less than, or pick a random number B that will be a less than N or equal to N. So then you'll get a set of F stars, a class of F star classifiers. So each F is going to represent a decision tree. And then to determine which output label wins, you use the majority voting. So that means that the one with the highest output, meaning like if I have from F of 1 to F of B, and I have the frequency, the one with the highest frequency of a specific class should win. Does that make sense?
Yeah.
Yeah. So bagging, why does bagging work? You're combining multiple classifiers to reduce the variance of the final classifier. So you're effectively reducing the number of features, but you're combining features to get the outputs. So that, like your base, like I can see why this works is because like you could have a total of, you can make a decision tree off of 5 features, or you can make 3 or 4 decision trees where you have F of 1 and F of 2, and then the others are random subsets of, or the original sample. And then you get outputs for each of those. So you kind of see how each of the original samples and their duplicates have an impact on the final outputs. So you can start to see which the randomness actually helps you identify which features are really important and which ones are not.
Yeah.
Right.
So for the classifier, so it says majority of the classifiers. So
Yeah.
does that mean that like yeah, what exactly does this mean? Does this mean like you're comparing the trees and you're seeing
Yeah.
which one occurs the most time?
Yes. So you can have f of b number, like the f of, you could have a b number of decision trees in your set. And
Right.
for each decision tree, like let's say I'm trying to identify if a data sample uh, is a blue marble, a red
Oh,
marble,
okay, okay,
or a
got it.
green marble. And so I see what they output, and I see that most of them, like say the like 60% of them outputted
Yeah.
blue marble. So there, that would win as the majority vote.
Yeah. Okay, got it.
Yep. And then let's see. So bagging is combining multiple classifiers, and you're reducing the variance of the final classifier. Um, and why would this be useful is when you have a classifier with high variance. So if you have a really bad decision tree initially, if you have one decision tree that has like high variance, which basically just means that a lot of these different events are equally likely, like these classifications are equally likely, um, it would be beneficial for you to create multiple trees that output with less number of features, get the outputs, and then come to consensus because there's less variance between that. So then bagging decision trees are also known as random forests. So here you're taking the data set S, you pick a sample size S star, and you replace some number of those samples of size N. You grow a decision tree TB, you repeat that B number of times, and the final classifier will be the majority of those outputs.
That's the same thing, right?
Yeah, this is basically just taking or saying what we were looking at, the example above, in words.
Okay.
So yeah, random forests. Uh, yeah, so they're almost identical to bagging decision trees, but we're going to add some randomness. Um, so what's happening is like, so bagged random decision trees are random forests. So this is basically saying that each of these, uh, you're picking M of the D available attributes. Oh, okay, yeah. So this is basically saying that if my original like data sample set or sample S had 10 features, I'm going to pick some random subset of those features at each split when I want to do the split, like when I want to grow the tree. So what that basically means is like, remember originally you would have your total sample size of S and you could have 10 features in it. You calculate the information gain for each of those features to determine which of the ones is the best attribute to split on. This is different. You're picking at each level that you're trying to calculate the best feature, you are just going to pick some random subset of those features, calculate the information gain from that, and select that as the best feature. And you'll repeat that for as many trees as needed, and that'll generate the random forest.
Hmm.
So there's a possibility that when you actually do do the subset of random features of your available attributes, you may not pick the best one out of the total set, but you would pick the best one of the subset of random values. Eventually, if you create enough trees, you would eventually get to the best solution. Yeah, so the hyperparameters are the number of randomly chosen attributes. So this is the rule of thumb. You just want to pick the square root of the dimensions or features or attributes. So yeah, I don't know why though, but I just know that you just do the square root of the number of dimensions you have or the number of features you have as m. Maybe KT, you know a little bit more about how this, like why that's the rule of thumb, or is it just, that's just why? Okay, cool.
I'm not sure, but it's a hyperparameter. You can tune it like any other hyperparameter.
Got it. So yeah, how to optimize M, cross-validation. So that would just mean that you would, cross-validation is basically you take your total data set and you create splits of training data, calculate, or you create a split between your test data and your training data, or your training data and your validation data. And then see how well it works, and then you just try different combinations of splits. And then the one that gave you the best, outcome would be the one that's the M that you would want to select. Is there an error, is there an error calculation for cross-validation?
Yeah, because the actual value, right? So you have some training set and some test set, and so you know the actual, and you know the predicted, and so the error comes from there.
Okay, so yeah, so we would do that. Yeah, and so B is the number of decision trees in the random forest. Yeah, okay, and so the last thing is you just keep adding trees until the training error stabilizes. So once you hit a plateau, then you know how many trees you need to have.
Okay.
Huh.
Yeah, random forests are pretty good. Pretty useful.
Here's my question. Shouldn't we be able to see, or maybe this, I'm asking a different question than what we're trying to solve, because we're trying to use a random forest to classify. But you should be able to see which attributes have the most information just by using principal component analysis. But
Yeah,
does it not always help us classify?
it's true, but the problem is that for small data sets that works. For large data sets, it's too computationally intensive to do PCA. So like you,
because
so
you,
like,
oh, I see. Yeah, okay.
yeah, because imagine you have like a data set that has 1,000 features, and that 1,000 features has like 100,000 data points for each feature. Calculating information gain for that is like ridiculously intensive.
Right,
Uh,
okay.
yeah, and so that's where the random forest comes in, is that you are going to select a subset of that 1,000 features with their 100,000 data points, and then you're able to create a tree for that, introduce randomness, which then already is creating a subset of those, like the total number, and then you just create as many different trees. It's like parallelizing your calculation, and then you take the outputs of all of them and use the majority rule to determine which output classification is the best for your forest. That makes sense?
Yes, but
Because eventually you'll get the answer that if you had built a decision tree of all of your 1,000 features and just did the whole computational part of it with the information gain, you would get to like, it's going to output a classification, right? It'll give you how to, like, what certain data points should be in what classifications. But with random forest, you still get that. It's just based on probability, like the frequency of subset of your features.
Okay, we should move on.
Oh, that's it. This is the end.
Oh, this is it?
This is the end. Yeah. Does that KT, did that make sense?
That last part?
Well, okay. What I mean is like, yeah, is there a better way to explain like why using a random forest would save you like computational?
It doesn't. It's more intense. But
It is?
yeah, because essentially a decision tree, a random forest is a series of, is it a series
trees.
or is this?
Yeah, it's a series of trees.
It's a series. Yeah, it's multiple decision trees. So whatever the cost of one decision tree, and let's say you want 50 trees in your random forest, then it's going to be 50 times as intensive. The reason you do random forest is because it's just the practicality of ensemble learning. So if you have a weak classifier, so if you have a model that doesn't classify very well, but let's say you use multiple of those models in an ensemble, using all those weak learners together in an ensemble makes it a stronger learner.
That's right.
So the randomness helps make the different learners different. So if you just use the same decision tree 100 times, it's going to give you the same answer every time, because these are decision trees are deterministic. So that randomness helps change each learner, and then you do a majority vote on those. But yeah, so it should be more computationally intense,
Okay.
or it should take longer. I would just say it's going to take each decision tree. It's about the same, and then you have to depends on how many trees you have in your forest.
Okay, that makes sense.
Bayon, my question, and I see now where I fucked up, is that, like, you know, one way to prune your data set to reduce, like, if you have 1,000 parameters, you
Yeah.
can do principal component analysis. So basically, you just evaluate your matrix and you say, actually, these 100 comprise 90% of the information of my matrix, so I'm going to focus on these. But
Yeah.
I guess the assumption here is that just because they have the most information doesn't mean they classify well. And so you
Right.
can use something like this instead.
That makes sense. Yeah. Okay. So you reduce your dimensions.
The thing about PCA though is that you lose your features. So I don't know if I've been missing a few lectures, but in PCA you're projecting your feature space onto a different feature space where the features that you think you have are no longer there. Then your new features are going to be linear combinations of your old feature space.
But you can. Oh, go ahead.
No, go ahead.
But you can, just by looking at the weights for each of your features, you know which features carry the most weight, and so you can look at how much information each feature carries individually without using your principal components, right?
Look at the weights. I've never done that. I don't know. Can you do that? That's cool.
I'm assuming. I actually don't know.
You just try it out. It's research.
Yeah, I've never done that. I mean, yeah, that sounds. If you could do that, that would change my understanding of it. But the way I understand it, that's not possible. I don't think. Let me think about that. Because it's all eigenvectors and eigenvalues. I don't know.
Yeah,
But
but I think the argument he's making is that you can use, because
you can just
PCA is supposed to like kind of like reduce the dimensionality of the features that you have. And so if you have like some features that are weighted more heavily by just looking at how the basically how it's constructed, how the PCA is constructed, then you can have some level of confidence that those features are the most important. And so maybe you just start with those instead of all the features, or randomly choosing features.
What Kevin is saying is, like, I think the weights come after you have switched your stuff, you projected onto a different.
Yeah, I've never heard that used for feature importance. I'm sure it's possible. I've never done it before though.
Okay. I'll look into it. I probably won't, but I'll write it down.
No, well, I'm looking into it right now.
Okay, well, let me stop recording then. I didn't realize it was, I thought it was going to be a lot.